Swayam Prabha. Digital India. Educated India.
Welcome to Organic Chemistry Paper 3. In Unit 3, we are studying about heterocyclic compounds. In Lecture 8, we are going to study about quinoline and isoquinoline. I am Dr. Balaji, currently working as Associate Professor in the School of Biotechnology. This project is sponsored by DTH Swayamprabha, MHRD, New Delhi. The topics that will be studied in this particular session include structural elucidation of quinoline. We will study how the structure of quinoline can be deduced. Then we will study about what are the different methods of synthesis of quinoline. The structural elucidation will be actually confirmed by these different synthetic methods. We will study about Gams synthesis, Scarp synthesis, Doebner-von Miller reaction, Gams synthesis, Friedlander synthesis, nor-quinoline synthesis. Then we will move on to study about structural elucidation of isoquinoline. So here we will also be studying about various synthetic methods by which isoquinoline can be made. Some of the methods include Pomeranz-Fritz method, Schindler-Muller modification, Bischler-Napieralski reaction, Pictet-Gams reaction, and Pictet-Spengler methods. Next we will look at quinolines and isoquinolines. Both quinolines and isoquinolines are polyaromatic systems, 6-membered polyaromatic systems containing nitrogen. There is actually one nitrogen that is present in these kind of heterocycles. The structures are given here. We have a bicyclic system here. The nitrogen is present at one position in the case of quinoline, and nitrogen is present at two positions in the case of isoquinoline. So these are 6-membered rings having one heteroatom. So these are polyaromatic 6-membered nitrogen heterocycles. And the another name given to these kind of compounds are benzopyridines, because this is the benzene unit. So this short name for benzene unit is benzo. So if you just look at this particular unit, this is only the pyridine unit, and that's the reason the name given is benzopyridine for this kind of compounds. And of course, now the position is actually little bit different in the case of this compound, but still these are called as benzene and pyridine combined together. So the common name given to these compounds are benzopyridines. These moieties are actually widely present, especially in the structural backbone of many naturally occurring alkaloids like papaverine, laudanosine, quinine, etc. All of them have a quinoline or isoquinoline type structural backbone. And biosynthetically, tryptophan is the starting material for quinoline, and tyrosine is the starting material for isoquinoline based alkaloids. So whatever is the alkaloids, when they have different quinoline and isoquinoline structures, tryptophan and tyrosine are the starting materials or biosynthetically starting materials for those kind of compounds respectively. And of course, as the structure is given here, tryptophan has a benzene ring with the nitrogen at the one position. That means it is just adjacent to this ring. So that is the reason tryptophan is the starting material, biosynthetic starting material for the formation of quinoline. And if we look at the tyrosine, this is the aromatic ring, and in the aromatic ring we actually have 1, 2, and only in the third position we have the nitrogen atom, but actually the ring is formed from this side. For the 6-membered ring formation, we need additional one more carbon units. So those one more carbon units may be formed from this side. So that's the reason we have the 6-membered ring isoquinoline moieties are formed from tyrosine biosynthetically. So here are some of the important quinoline and isoquinoline structures given. As we have seen, quinine is having a quinoline structure, and pefoxycin is having a quinoline again structure. So this is the basic quinoline moiety. and chloroquine is also having the quinoline moiety. So, the top 3 compounds are having the quinoline moiety, and when we look at papaverine has the 1, 2, the second position the nitrogen atom is present. So, this is a isoquinoline type moiety, and here reticulin also the nitrogen is present at the 2 position. So, these kind of compounds are derivatives of isoquinoline. Quinapril also has the same structure. So, if we start from here 1 and 2, the second position the nitrogen is present. So, this is our isoquinoline unit. So, these compounds are important alkaloids. So, let us look at the structural elucidation of quinoline. The quinoline has C9, that is 9 carbon atoms are there, and the molecular formula is C9H7N. And quinoline like indole does not undergo addition reactions, that means it does not undergo addition reaction with halogens or HX, and it also does not decolorize alkaline KMnO4 or bromine water. So, what these things actually mean is basically there is no double bond in this kind of compounds. See, whenever an addition reaction has to occur, we need to have a polyphenic double bond. So, whenever there is polyphenic double bond, they undergo addition reactions. So, if hydrogen is added, or maybe if X2 is added, then we end up with a compound like this. So, X will be added to these 2 carbon atoms. So, the addition reaction actually leads to that final product. So, since quinoline does not undergo addition reaction, there is no polyphenic double bond in this compound. Similarly, decolorization of KMnO4 is also an example of addition of OH unit across the double bond. So, that also does not happen. In other words, there is no polyphenic double bond in quinoline. But it does undergo electrophilic substitution reactions like sulfonation, nitration, halogenation. So, whenever there is a electrophilic substitution occurring in the system, then we can say there is a aromatic ring present in that particular compound. So, that way we can say quinoline has at least one aromatic ring. And this also undergoes a nucleophilic substitution reaction. So, in the earlier sessions we studied about pyridine, where the pyridine ring can undergo nucleophilic substitution, whereas the benzene ring can undergo electrophilic substitution. So, the presence of nucleophilic substitution reaction, or the compound undergoing nucleophilic substitution reaction, is an example of the presence of pyridine ring. So, sodamide when treated with quinoline leads to the introduction of the amino groups. So, this is an example to tell that the compound quinoline has 2 type of ring structures. One is the benzene ring structure, another one is a pyridine ring structure. So, this is a hint for us to deduce what is the actual structure of quinoline. And let us continue with other studies also, because we only now know 2 rings are there. One is a benzene ring, another one is a pyridine ring. How they are connected, all these things we are not aware of. Now, we are going to deduce that one by one. So, quinoline when treated with alkaline KMnO4 leads to, or vigorous oxidation leads to pyridine 2,3 dicarboxylic acid. So, this clearly tells that one of the ring is the benzene ring, which would have underwent oxidation, because we end up with a 2 carbon acid, that means oxalic acid is also formed. So, total if you look at there are how many carbon atoms are there, we had so we know there are 9 carbon atoms that are present. So, in the pyridine case we have actually 5 carbon atoms within the ring, and there are 2 additional carbon atoms in this carboxylic acid unit. So, 5 plus 2, 7 carbon atoms are there, and the formation of oxalic acid actually tells additionally that 2 more carbons are present. That means total 9 carbons can be easily accounted for. So, this clearly tells like there is one pyridine ring and there is maybe possibly a benzene ring. And quinoline alkaloids can be biogenetically derived from anthranylic acid, because we also saw earlier in the case of indoles, anthranyllate is a starting material for indole type compound also. So, here again we can also look at there we have a 6 and 5 membered ring in the case of indoles, but here in the case of quinoline we have a 6 plus 6 membered ring. So here again the starting point is the anthranoelic acid derivative. So the anthranoelic acid is the biogenetic starting material for quinoline type alkaloids. And further studies have shown that formation of the quaternary ammonium salt with one equivalent of alkyl halide. So that tells there is a tertiary nitrogen atom that is present in this kind of compound. So if you look at the pyridine nitrogen, this is the tertiary nitrogen, and this can undergo addition with one equivalent of alkyl halide. So exactly one equivalent only this undergoes alkylation. So that means there is a tertiary nitrogen that is present. If more than one equivalence of the alkyl halide is used, then depending on that we can actually identify whether it is a primary, secondary or tertiary nitrogen. So from the oxidation studies and biosynthesis, we can conclude that there are two rings that are present and nitrogen is present in position number 1. So this we will confirm like how, because in the case of anthranoelic acid, if this is going to be the biogenetic starting material, then obviously the amine and the carboxylic acid are in the ortho position. So that means this is the starting point for the amine. The nitrogen comes from one place and then adjacent position we have to have a carbon. So that means nitrogen is in the position number 1. So that we can actually deduce how we are getting this particular product. So based on all these things what we have discussed, we can draw actually 9 different structures for the quinoline moiety. So let us look at what is the actual moiety and what are all not possible. All those things we will now find it out. So the quinoline undergoes vigorous oxidation to give the pyridine dicarboxylic acid. So out of all these structures, if you look at what are all the structures which can give the pyridine dicarboxylic acid is, so this compound can actually give pyridine dicarboxylic acid. This one it's a little bit difficult, but still we can assume that it is possible. But in the case of C, it is not possible because the nitrogen is in the second position. So this will not give the pyridine, this may give the pyridine dicarboxylic acid, but they are not the, if this is the number 1, this is number 2, this is number 3. So 2,3 dicarboxylic acid is not possible in this particular case. So this is not the structure. And in the case of D also, we can rule out that the 2,3 dicarboxylic acid is not possible. So this is not the structure. And 5 also, 5 we have a possibility that there is a nitrogen here. So this bond and this bond, when they undergo oxidation, we can still get the 2,3 dicarboxylic acid. So this is a possible structure. And in all these cases, we were having the nitrogen on the 6-membered ring. There is also possibility that the nitrogen can be on the 5-membered ring, but if the nitrogen is on the 5-membered ring, then we cannot get this pyridine type product. So that means even though these are possible structures where the nitrogen is on the 5-membered ring, this cannot be the structure for quinoline because oxidation of this will not give pyridine 2,3 dicarboxylic acid. So F and G are not possible where the nitrogen is in the 5-membered ring. And then we also have structure H and structure I. So between these two structures, we can say actually the structure of quinoline is going to be I, because this is the one position the nitrogen is present. In structure H, we have nitrogen on the 2 position. So we already know that 2,3 dicarboxylic acid cannot be formed from the 2 position structure. So we can also rule out this one. So from all these things, we can actually conclude that the structure may be 1, that means I, A or B. So these are all, even E is possible for this particular case. But if we look at the other structures, we have a exocyclic double bond in this particular structure B. We have a exocyclic double bond in the, although this is in conjugation, this is still considered like a outside of the ring. So that means these kind of double bonds can easily undergo addition reactions. So the external double bonds are not, when they are not present inside the ring, so they cannot, they can easily undergo addition reactions. So these structures are not actually possible, because in the case of quinoline, there is no addition reaction. So that rules out the structure for the compound B. And of course, there is one more example is like we have seen these compounds undergo aromatic electrophilic substitution reaction. So of course, if we have a pyrrole ring, then there is a possibility that they can undergo aromatic electrophilic substitution, but the nitrogen is present in the 6-membered ring, then aromatic electrophilic substitution cannot be explained by this particular structure. So if we have structure A or B or E, all these three structures cannot explain the aromatic electrophilic substitution of quinoline moiety. So we can completely rule out these structures for quinoline. Then finally we can confirm that the structure of quinoline may be given as in I. And finally we can carry out the synthesis to confirm the structure of quinoline. So here are some schemes by which quinoline can be synthesized. We have given various examples, but in all the cases anilines, especially the ortho substituted anilines or the aromatic primary amines as the nucleophilic nitrogen donating component are the most important reaction. So if you look at in all the cases, the starting material is in this particular case the aromatic ring with the nitrogen, that means aniline is the starting material. The dotted line is the place where the connection takes place later on, that means during the synthesis we are connecting these two positions later on. So this is the starting material, means this is nothing but aniline. And here again we can actually say this is a substituted aniline. And if we look at this one, this is a ortho substituted aniline again, and here again or in all the structures we can actually say the starting material, that is the nitrogen is actually present with the benzene ring. That is the most favorable starting material for the synthesis of quinolines. And we have the other unit, say for example we are having a 2-carbon unit, or we have a 3-carbon unit that is getting attached to this one. So this can be most of the time an electrophilic 3-carbon unit, that is usually a carbonyl compound, can be the second counterpart for the formation of quinoline moiety. Let us look at some of the important methods for quinoline synthesis. So the first one is the Gams synthesis. So in this reaction there is a condensation of aromatic primary amine, that means as we have seen aniline is the starting material. So this condenses with the dicarbonyl compound. So it can be a beta diketone or it can be a ketoaldehyde also. So one of this methyl group can be hydrogen or it can also be a alkyl group. So that means it is a beta diketone or beta ketoaldehyde. These two undergoes condensation to give the, this is the ene, this is the amine. So this condensation leads to the formation of enamine intermediate, and once the enamine intermediate is formed, this can actually undergo cyclization in the presence of a strong acid to give the 2,4-disubstituted quinoline derivatives. And when we have a meta-substituted aniline, so that means meta-substituted means when we have some substituents on this position or some substituents on this position, they lead to regioisomers. That means two different ortho ring closures are possible. That means the cyclization can happen at this position or it can happen at this position. So based on that we end up with the regioisomers when Gams synthesis is carried out. Let us look at the mechanism for this reaction. So as we mentioned, the main thing is the formation of enamine. The enamine intermediate formation is a crucial step in this reaction. So how this actually happens is in the presence of acidic medium, because this reaction is carried out under acidic medium. So the protonation of the carbonyl oxygen takes place. So this is the initial step, and then this electrophilic carbon is being attacked by the lone pair of electrons from the nitrogen. So we end up with this particular intermediate, and this hydroxy unit is lost as a water molecule after the proton transfer. So once the proton transfer takes place, we end up with the H2O plus ion, and this is easily lost, and another loss of proton leads to the imine as shown here. The imine undergoes imine-enamine tautomerization. So here one of the hydrogen is shifted from this particular carbon to this particular nitrogen. So we end up with the enamine, and this is protonated. That means the carbonyl unit is protonated, and once this is protonated, the aromatic ring pi electrons attack this particular electrophilic carbon atom, leading to the cyclization, and this cyclization, the hydroxy unit is formed as the intermediate, one of the intermediate, and this hydroxy unit is lost as a water molecule, and this leads to the final product of quinoline as shown here. So of course there is a proton, loss of proton takes place, which finally completes the reaction to give the quinoline derivative. So this is how the overall reaction actually proceeds. The crucial intermediate in this reaction is the enamine from the starting aniline and the carbonyl compound. Next is the scrub synthesis. So in this reaction, an arylamine, again we start with the aniline unit. The aniline reacts with the alpha beta unsaturated carbonyl compound. So these two undergo reaction. So what is the reaction they undergo is simply the condensation reaction, and we have already seen this is similar to a Michael addition. So this condensation in the presence of heat leads to this particular intermediate, and this on oxidation, first it has to undergo cyclization, because this aromatic ring is basically electron rich. This carbonyl carbon is electrophilic, so this pi bond can attack this carbon, and that leads to the cyclization, and finally oxidation of that intermediate leads to the final product. So here acrolein is the one that is the intermediate involved in this product. That alpha beta unsaturated compound is nothing but an acrolein, but this acrolein undergoes polymerization very readily. So that's the reason we cannot prepare and store it for longer time. So here in this particular case, the reaction is carried out in the presence of acid. So that means the acrolein is actually formed in situ from glycerol. So the starting material is not acrolein, but the starting material is glycerol. So the reactions are given here, how the glycerol is converted to acrolein in situ. So the glycerol has 3 hydroxy groups, and initially protonation takes place, because this reaction is basically carried out in the presence of a strong acid. So the protonation takes place. One of the hydroxyl unit, especially in this particular case, the central hydroxyl abstract that proton, or the proton adds to this OH group. So we end up with a H2O plus ion that is formed. So one of the hydrogen from the neighboring carbon is lost, that leads to the double bond formation as shown here, and the second hydroxyl abstract a proton, another proton there. That means addition of one more proton happens to this hydroxyl group. So we end up with the H2O plus ion, and once the H2O plus ion is added to this hydroxyl group, this loses one of the hydrogen atom, and the shift of the double bond leads to the formation of acrolein. So this acrolein is formed in situ, and this formed acrolein undergoes further reaction. So as I mentioned, this particular reaction is a Michael addition reaction, especially since the nitrogen is involved. This reaction is actually called as a azo-Michael addition reaction. So this is the first step. This leads to the formation of this particular intermediate, and once this intermediate is formed, the next step is basically the tautomerization. So we have the ene group here, and we have a all here. So this ene and all undergoes tautomerization to, in this particular case, to give a aldehyde unit. So this tautomerization leads to the formation of the aldehyde unit, and the next step is, as I mentioned, an intramolecular acylation, aromatic electrophilic substitution. That means this pi electrons attacks this electrophilic carbon atom, leading to the cyclization. So we end up with a hydroxy unit, and this hydroxy unit undergoes dehydration to give the double bond, and finally oxidation leads to final product, quinoline is formed. So these are all the overall reaction steps in the scrub synthesis of quinoline. Next is a Doebner-Miller reaction. So in this reaction, if you look at this is very similar to the previous reaction. In the previous one, we have a hydrogen atom here, that is acrolein was used as a starting material. In this case, we have a alpha beta unsaturated carbonyl ketone is present, and in the previous case we have just used the heating. Here we have a Lewis acid, zinc chloride, or FeCl3 is used as this reagent for facilitating this reaction. So if you look at the number of steps, it is very similar to the scrub synthesis. And finally we end up with substituted quinoline after oxidation. So the major difference between scrub synthesis and Doebner-Miller synthesis is, since we are having a substituent, that means a ketone is used, whatever is the substituent that is present here is going to be introduced here as the alkyl unit. So that is how we can actually prepare a substituted quinolines using this particular method. And the next one is Gams quinoline synthesis. So in this particular case, orthoacyl aminoacetophenone. So this is the acetophenone unit. If you look at simply, this is acetophenone. So there is a acyl unit, amido unit that is present in the ortho position. So orthoacyl aminoacetophenone is the starting material. This, in the presence of a strong base, is transformed to the cyclic product. That means we end up with the 2 hydroxyquinolines, product A and product B. 2 types of products are possible. So this is another method of preparing quinolines. The next one is the Friedlander synthesis. So in this particular case, 2-aminobenzaldehyde is treated with the ketones, and this condensation leads to loss of 2 water molecule and substituted quinolines are formed. So whatever is the substituent that is present on the carbonyl unit, they are actually present here. So that means depending on what is the ketone we are starting with, we will end up with the corresponding alkyl substituted quinolines. And another method is 2-amino-aryl ketones. So this is the amino group is present in 2 position, and this is the aryl ketone. So 2-amino-aryl ketones can be converted to quinolines. So there is one method which is carried out under acidic conditions. That means sulfuric acid, acetic acid heating leads to the substituted quinoline derivative. Another one is a basic condition. So we can use 2 different conditions, either it is acidic or basic conditions, to form the corresponding quinoline derivatives. And if you look at the starting material and the product that is formed, whenever we use ethanol in this particular case, this ethyl unit is actually introduced into the final product, and when we use acetic acid, the methyl unit is actually introduced into the final product. So this is the major difference, and here again another methyl group is being introduced in this particular case. So use of acetic acid introduces 2 methyl groups, and the use of ethanol in the basic condition introduces 1 ethyl group. So depending on how many substituents we want, we can actually choose, and the starting material is one and the same. That is 2-amino-aryl ketone is the starting material that can be converted to substituted quinolines under acidic or basic conditions. Next one is the norquinoline synthesis. So in this case, formation of alpha hydroxyquinoline. So this is the alpha position, and in this position we have a hydroxy unit. So the formation of alpha hydroxyquinoline from beta ketoesters and arylamine. So this is our arylamine, and this unit is the beta ketoesters. We have a carbonyl unit, we have a ester unit. So the carbonyl and esters are in beta position. So, that is the reason this is called a beta ketoester. Heating these two compounds at 130 degree leads to this particular intermediate. This can be cyclized using sulfuric acid as shown here. That leads to the pyridone derivative. So, this is a 2-pyridone derivative. So, this 2-pyridone derivative undergoes tautomerization to give the corresponding hydroxyquinolines. So, here the initial intermediate formed is the anilide derivative. So, the cyclization of this anilide, which is a electrophilic aromatic substitution reaction, and this cyclization can be effected by acidic reagents like sulfuric acid, or PPA is nothing but polyphosphoric acid, and both these reagents, any one of the reagent can be used, and of course use of polyphosphoric acid generally gives a cleaner product in these kind of cyclizations. And final dehydration can be effected by concentrated sulfuric acid, and this gives basically the 2-pyridone derivative, which can undergo tautomerization as we mentioned. So, when we studied in the beginning of heterocycle formation, we also studied about the driving force for the heterocycle formation is this particular tautomerization reaction also. So, here we have a aromatic system, whereas in the case of pyridone we do not have an aromatic system. So, that is the reason the formation of the aromatic system is the driving force for this particular tautomerization reaction. So, once this carbonyl, that is the pyridone is formed, 2-pyridone is formed, this can very readily undergo tautomerization to give the aromatic product, that is the alpha hydroxyquinoline. Here are the snapshot of what are the different ways by which quinolines can be prepared from aniline. So, our starting material in most of the cases what we have seen is aniline only. So, the aniline can be converted to quinoline using Gomes method. So, here we have the beta dicarbonyl compound is generally used, and in the Conard-Limpand synthesis we are using beta ketoesters as the starting materials along with the anilines, and in the Doebner-Funmehler reactions or Doebner reactions we have two different intermediates. So, we can use an aldehyde and alpha keto acid can be used. These two can be condensed with aniline to give corresponding quinoline derivative, that is a Doebner reaction, and if we use alpha beta unsaturated compound, especially acrolein or similar derivative, that is a Doebner-Miller reaction. And in the scrub synthesis we are not using the alpha beta unsaturated compound directly, but we are using the corresponding glycerol to prepare the alpha beta unsaturated compound in situ. So, that method is called the scrub method, and Gold-Jacobs method also can be used to convert anilines to the corresponding quinolines. Let us move on to the next one, which is the structural elucidation of isoquinolines. So, the isoquinolines also have the formula like C9H7N, very similar to quinolines. These are more basic than quinolines. So, this is one difference, and here again isoquinoline does not undergo addition reactions similar to quinoline. So, that means there is no isolated double bond in the case of isoquinoline also. They also do not decolorize KMNO4 or bromine water, and this undergoes electrophilic substitution like very similar to benzene type molecule. So, that means there is a presence of aromatic ring is seen in these kind of compounds, or these compounds has aromatic ring very similar. These compounds undergo electrophilic substitution reaction like sulfonation, nitration and halogenation reaction. So, this shows there is a presence of an aromatic ring. These compounds also undergo nucleophilic substitution similar to pyridine ring. That's it also shows that there is a presence of pyridine ring. And the vigorous oxidation gives pyridine 3,4-dicarboxylic acid and phthalic acid. So, these are all the two different carboxylic acids that are formed on vigorous oxidation. So, this shows that one of the benzene ring has there is one benzene ring and there is another nitrogen containing ring. So, these are all the two clues we are getting through the oxidation reactions. And from the oxidation studies, we can conclude that there are two rings and the nitrogen is present in two position, because when the nitrogen is present in two position only, we will actually get a compound. So, if we start from here, this is position number 1, this is position number 2, and the ring is actually present here. So, when the ring is present like this only, in the second position nitrogen is there, that on oxidation can give 3,4-dicarboxypyridine 3,4-dicarboxylic acid, and the formation of quaternary ammonium salt with one equivalent of alkyl halide shows that this is a tertiary nitrogen, and the biogenetic source for isoquinoline is basically the phenylalanine and tyrosine. So, these two can be converted to the corresponding isoquinoline structures. So, that means here there is no nitrogen present at one position, but it is further from that one position. So, in other words, actually this is how this particular part of that ring actually cyclizes to give the isoquinoline derivatives. So, here there is one additional carbon that is present here. So, that clearly tells that the second position is occupied by nitrogen. So, based on the reactivity, what we can deduce is there are various possible structures like A to E are possible for isoquinoline, and let us look at what are all the structures that actually can be used to confirm the structure of isoquinoline. As we know, structure A is not having the cyclic 2 benzene ring structures. Other structures, if you look at the structure B and the structure D, there is a exocyclic double bond, and these compounds do not have an aromatic ring. So, if you look at the structure A, B and D, they do not have a aromatic ring. So, when there is no aromatic ring, then we cannot explain how isoquinoline can undergo aromatic electrophilic substitution reaction. So, that means, in other words, what we can say is the structure A, B and D are not a probable structure for isoquinoline, because they do not have the required aromatic ring system, but they do have the pyridine like system. So, here is a pyridine unit, here is another pyridine unit, and this also has a pyridine unit, and in both the places it is actually at the 2 position the nitrogen is present. So, although the pyridine ring is at the right way it is present, but the second aromatic ring is not present. So, we can completely rule out the structure for A, B and D for isoquinoline. Now, we are left with only two structures, C and E. If you look at C and E, the compound isoquinoline is more basic than quinoline, and we already know in the case of quinoline the nitrogen is at position number 1. So, that means in the case of isoquinoline it cannot be at the position number 1. So, it is at the position number 2, because with this we can explain there is a aromatic ring, and this aromatic ring can undergo aromatic electrophilic substitution reactions. So, when we oxidize this, this will lead to phthalic acid. So, the formation of phthalic acid can be explained if we have these two 6-membered ring structures for isoquinoline. And if we look at the other oxidation product, this particular bond and this bond can undergo breakage to give the corresponding 3,4 substituted. When we write the number, this is 1, 2, this is 4. So, 3,4 pyridine dicarboxylic acid is formed, can be explained by this particular isoquinoline structure where the nitrogen is present at 2 position. So, by these kind of reactions we can actually deduce the structure of isoquinoline, and of course, we can carry out the final synthesis of isoquinoline to confirm the structure. So, the first reaction is the formation of Pomeranz-Fritsch synthesis method. So, here an aminoaldehyde and an aldehyde is reacted to give the isoquinoline derivative. So, here the intermediate is the iminoacetal intermediate. So, this iminoacetal, the reason is whenever we take a aminoaldehyde, aminoaldehydes are extremely aminoaldehydes undergo self-condensation. So, that is the reason for this particular synthesis we cannot directly use aminoaldehyde as a starting material. So, this aldehyde unit is actually protected as the acetal unit. So, the iminoacetal intermediate is actually used as a starting material. So, this is now reacted with the second molecule of aldehyde. That means one aminoaldehyde is treated with another aldehyde unit, and these two undergo condensation. So, that means we have the benzaldehyde that is used here. So, this is the benzaldehyde part, and this is the iminoacetal intermediate that was formed from the aminoaldehyde. So, these two can easily be condensed in the presence of, that means benzaldehyde when treated with this corresponding amino compound, these two can form the imine derivative, and once this imine is formed, on treatment with the sulfuric acid, we end up with a carbocation on this particular carbon. So, when there is a carbocation, this benzene ring pi electrons can easily attack this electrophilic carbon atom carbocation, leading to the cyclization, and this cyclization actually finally gives the corresponding isoquinoline unit, and this OET unit is lost as a ethanol molecule. So, we can also use dialdehyde and amine. So, instead of aminoaldehyde and aldehyde. So, if we look at what are the required units that are required for the isoquinoline synthesis, is we need a amino unit. One amino unit is required, another aldehyde unit is required, another aldehyde unit is required. So, that means we need two aldehyde unit and one amino unit. So, that the permutation combination what we can do is, we can have aminoaldehyde as one unit and aldehyde as another unit. This is one type of reaction. We can also have the reverse of that. That means both aldehyde on the same compound and the amine can be a separate one. So, these are all the two different ways by which we can actually prepare isoquinoline. That means different starting materials can be used to prepare isoquinoline. The Schilter-Muller modification is actually shown here. So, in this particular case, benzyl aminoacetal, this is actually formed from the benzylamine and the glyoxal semiacetal. So, this is the glyoxal semiacetal and this is the benzylamine. When these two condense, we end up with the benzyl aminoacetal. So, this is the benzyl aminoacetal. This can undergo cyclization in the presence of acid. So, that means we can also use sulfuric acid or similar acid. Use of sulfuric acid actually facilitate this reaction, because in this reaction the side product is ethanol unit, and this ethanol can be easily removed when we use sulfuric acid at a high temperature. So, that leads to substituted isoquinoline derivatives. So, whatever is the substituent that is present in the starting benzylamine is retained in the final product. So, we can actually get the required substituted isoquinoline through this method. The next one is the Bischler-Napieralski reaction. So, in this reaction we are starting with the 3-phenylethylamine. So, this is our starting material, and if you look at the structure of isoquinoline and this compound, especially the 3-phenylethylamine, we are just missing 2 carbon unit, that is 1 carbon unit that is actually missing in this entire thing. So, this if it is connected, then we end up with the final product. So, how do we do that? The simple thing is, we are treating this with the phosphoryl chloride, and this is treated with acyl chloride. So, any of the acyl chloride is treated, that leads to the acylation on the nitrogen atom. So, this is the first step that happens, and once the acylation actually takes place, then the cyclization actually takes place. There is a pi electron rich aromatic ring is there, and the electrophilic carbon is there. So, this cyclization very well leads to the corresponding hydroxy derivative, and in the presence of a dehydrating agent, this hydroxy derivative loses water molecule, then we end up with a double bond, and once we end up with this double bond, treatment with the pelletized carbon leads to the final product. So, the dehydration of this particular intermediate leads to our final isoquinoline derivatives. Another one is the Pictet-Gams synthesis. So, in this reaction this particular intermediate, if we look at what is the compound, this is the amino unit, and this is nothing but the same 3-phenylethylamine unit, and this 3-phenylethylamine is actually acylated, and this is the corresponding acylated unit that is present. And this, when treated with P2O5 and xylene, undergoes reaction, especially the intermediate that is formed is a styrylamide intermediate, and this leads to the final, there are 2 water molecules that is lost in this particular reaction, and that leads to the formation of isoquinoline as shown here. So, how this Pictet-Gams reaction works? Basically, we have the, if we look at this structure, we have OR2, and here the OR2, the second one is actually hydrogen. So, we start with the hydroxy unit. So, when we start with the hydroxy unit, the first one and the foremost reaction is the loss of water molecule, because we are using a dehydrating agent and we are also heating this reaction. So, the loss of water molecule is the initial step. So, that leads to this particular intermediate. This, when treated with H3PO4, that means loss of H2PO4 minus takes place. What happens is basically the protonation of this particular acyl carbon takes place, and that leads to the cyclization, required cyclization, and when the cyclization takes place, we end up with a hydroxy unit, and this hydroxy unit here, this ring becomes non-aromatic. So, once it is non-aromatic, that is quite unstable. So, the loss of proton leads to the aromatization of this unit, and the hydroxy unit is lost as a water molecule by the shift of hydrogen, that is internal proton transfer from this nitrogen to this particular hydroxy unit leads to the loss of water molecule, and finally we end up with the isoquinoline derivative. So, here the N-acetyl 2-hydroxyphenylethylamine is the intermediate that is involved. Actually, this compound is the N-acetyl 2-hydroxy, because there is a acetyl unit that is present in the nitrogen unit. So, that is the N-acetyl unit is present, and here the hydroxy unit is present, because this compound, if you look at this is nothing but the phenylethylamine. So, the structure of phenylethylamine is this is our phenylethylamine. So, this is number 1, this is number 2, and in the second position we have a hydroxy unit. So, this compound is the N-acetyl, and also we have the acetyl unit on this particular carbon. So, we have 1 hydrogen less, and we have a methyl group here. So, this compound is N-acetyl 2-hydroxyphenylethylamine, and this is the starting material for our cyclization. And the next one is the Pictet-Spengler reaction. So, in this reaction, 2 aryl ethanamines. This is very similar to the phenylethylamine whatever we have seen. Here we have a substituted one. So, there is a substitution that is present in this compound, and this is when treated with aqueous formaldehyde leads to the imine derivative. So, the imine is the first intermediate that is formed, and treatment with the second aldehyde unit leads to 1,2,3,4 tetrahydroisoquinoline moiety after cyclization, and this can be converted to the corresponding isoquinolines after treatment with palladium carbon. Dehydrogenation leads to the final isoquinoline derivatives. So, if you look at the previous all the reactions, most of the reactions have a 3 unit that is generally used. There is a amino unit, there is an aldehyde, and there is also another aldehyde. So, 2 aldehyde units are actually used along with 1 amino unit, and here again if you look at this Pictet-Spengler reaction, this is also having the same 3 components. So, we start with an amine, and we are adding a corresponding 1 aldehyde is added, then we are adding the second aldehyde. So, depending on what is the first and the second aldehyde, we can have different substitutions. So, instead of benzaldehyde, if you use some other substituted aldehyde, then the corresponding substituent will be present at 1 position. So, this is another example of isoquinoline synthesis. And the same reaction can also be carried out with the acylation of the amine to form the intermediate N-acyl iminium ion. So, this N-acyl iminium ion is a crucial intermediate. So, once this is formed, this can also undergo, this is a very strong electrophile. So, the double bonded electrons from the aromatic system can very well attack this acyl iminium ion, leading to the cyclization. So, this cyclization step is a very crucial step. It can be very easily carried out when we have the N-acyl iminium ion. So, that means there is a one acyl unit is attached to the iminium ion. If you look at this imine, so this is our starting material in the previous process. So, here this imine is not highly electrophilic in nature, but the moment we put a electron withdrawing group, because the carbonyl unit, especially the acyl unit, is electron withdrawing in nature. So, that makes this nitrogen even more electrophilic in nature. So, when this becomes highly electrophilic, the pi electron, the double bond from the aromatic ring, can easily attack this electrophilic nitrogen. So, that leads to the cyclization, and this is another method by which we can actually prepare the isoquinoline derivatives efficiently. Let us recap in the summary what we have studied so far. We have studied about the structural elucidation of quinoline. So, how the structure of quinoline can be deduced, we have seen. How the electrophilic aromatic substitution reaction and the nucleophilic aromatic substitution reaction can be used to identify the two ring structures, both the aromatic ring and the pyridine ring we have studied. And we have also studied about the oxidation product, and based on that how we can reduce the structure of quinoline we have studied. We have also carried out couple of quinoline synthesis. The first one is the Gomes method, then we studied about Scrapp's method, Doebner-Miller method, Gams method, Friedlander synthesis and norquinoline synthesis are the various methods we have studied about. Then later on we studied about the structural elucidation of isoquinoline. Then finally we confirmed the structure of isoquinoline using synthetic methods. We studied about Pomeranz-Fritz method, Schlitter-Muller modification, Bischler-Napieralski reaction, Pictet-Gams reaction, Pictet-Spengler methods. These are all the various methods for the isoquinoline synthesis we have studied. With that, we conclude this session. Thank you.